Let us continue with the previous topic. In our last lecture, we introduced induction motor starting circuits using a Dol starter, which is capable of providing short circuit protection, overload protection, and undervoltage protection for a three-phase induction motor. Today we are going to discuss on the reducing the starting current of a three-phase induction motor. As we know, the starting current can be reduced by adding external resistances in the rotor side for on rotor case. However, this method is not possible for squirrel cage. So we can say the reducing starting current for on rotor is possible by adding external resistance. At the rotor side. This method is not possible for squirrel cage case. So let us modify our previously designed starting circuits in order to reduce the starting current as well. That starting circuit will provide us the short circuit protection, overload protection, and undervoltage protection, as well as it will have the capability of reducing the starting current both for on rotor cage and squirrel rotor cage. Suppose this is the three-phase induction motor. We have three connections. First of all, like the previous case, we'll have a switch. Then we'll give a connection for fuse. This is F1, fuse 1. Next, we have magnetic conductor M1, as you remember from the previous lecture. Next, we are going to introduce a resistor, that is extra resistor, in order to reduce the current flowing through this. Then we have overload heaters, and finally it will be connected with this. This resistor is a variable resistor. This is connected in a way when this terminal is connected with the leftmost terminal of this resistor, the complete value will be added. Complete value of the resistor will be added. Now we'll take another connection from here with a contactor, another connection from here with another contactor, and another connection from here with another contactor. All these sides will be shorted. Now these contactors are shorted when the corresponding magnetic coil is energized. Now when these contacts are open, what will happen? The current will have no other way but to flow through this complete resistance. Now if you connect this contactor, what will happen? The current will flow through this smaller amount of resistance. Now if we connect this line or this contact, then what will happen? Current will flow through this portion of the resistor. That means it will experience lesser amount of resistor. Finally, if we connect this contact, then current can flow directly through this line, bypassing the resistor. So initially, when we want to reduce the starting current, the complete resistor will be activated. Finally, under the complete running condition, all this resistor will be removed in a way by giving a connection on this contactor. So in this way we can add variable resistance in this line. Similarly, let us draw the same for other two phases. This is M2. Same resistor. This is fuse 2 for short circuit protection. And we'll be having three contactor here. like this. For the third phase, next we'll add Dol Starter. You can use the connection from these two phases. First of all, there will be overload contactor. Then we are going to have this magnetic coil. This is the start button, push to start. So let me write start here. And this is the stop button, push to stop. So normally they are connected, normally this is open. And we'll have another magnetic contactor that is named as M4. So when this start button is given, coil will be energized and M4 will be short circuited. That will keep the coil energized. Here additionally we are going to use time delay relays. What is time delay relay? The relay that is activated after a certain period of time, meaning that when they are energized there is a set time delay before their contacts shut. Let me show you, then the things will be clear to you. Here in parallel with the magnetic contactor we are going to take some connections. We'll have another M contactor that is named as M5, which is normally open and gets the connection when this M coil is energized. And here we are going to use one time delay relay, that is 1 TD. We are naming it 1 TD. What is the function? When the coil is energized and this line is shorted, when this 1 TD gets connection after a certain period of time, then it is energized. It is not energized instantly. So what will happen when this 1 TD is energized? If we write this contactor as 1 TD, 1 TD and 1 TD, after that certain period of time these contactors will be closed. We are coming to the operation part later on. Let us put another time delay relay. So here the contactor that will depend on 1 TD and another time delay relay that is named as 2 TD. That means time delay relay number 2. And these contactors are dependent on 2 TD magnetic coil. Similarly, let us draw another time delay relay, that is time delay number 3 TD, and this contactor depends on twice TD, and this contactor will be 1 when time delay relay number 3 will be energized. Now let us see the operation. When the start button is pushed in this circuit, the M relay is energized and power is applied to the motor as before. So power will be supplied because M1, M2, M3 and M4, they are energized and they will give a contact. But since the time delay number 1, time delay number 2 and time delay number 3 contacts are all open, the full starting resistance is in series with the motor, so that will reduce the starting current. So in this line we have full resistance, in this line in the second phase we have full resistance because they are open, so current must pass through this line in this direction. So full resistance will be applicable for this case. Now when M is energized, then M5 will also be closed. As M5 is closed, suppose this time delay relay has 1 second delay. That means after 1 second, this coil will be energized. So initially when you switch on the motor, initially to reduce the starting current, the full resistor will be applied, and that will reduce the current flowing through each phase. Now after 1 second, once the motor gets some speed, what will happen? This 1 TD will be energized, and that will make this 1 TD, 1 TD and 1 TD lines shorted. So current will start flowing through this path to this line. So the each line will get reduced amount of resistance. So the current value will be increased. Now as long as 1 TD is energized, this line will be closed. Again, this 2 TD will require some time to be energized. When after 1 second this one is energized, so current will start passing through this line and this line. Then after 3 second, 3 TD, that means time delay relay number 3, will be energized, and that will make a complete shorted path bypassing this resistance for the current to flow. So in this way we can have reduced starting current, and under running condition the full load current can be passed bypassing the resistance into the motor. So we can reduce the starting current by employing this dual starter having this type of resistance controlling method. Now let us solve some mathematical problems. A 208 volt 3-phase 4-pole. 4-pole means 4 pole per phase. 50 Hz induction motor. 50 Hz means the supply current is having 50 Hz. Induction motor is running at a slip of 4%. First question, what is the synchronous speed of this motor? For the first question, we know the synchronous speed N is equal to 120 F. F means supply frequency. Let me denote it by F1 over P. So P is 4 pole per phase case. That means the number of pole per phase. F1 equal to 50 Hz, which is the supply frequency. If we put all these values, the value of synchronous speed can be figured out. 120 into 50 over 4, that will give us 1500 RPM, rotation per minute. Next question is, what is the rotor speed of this motor at the full load? Motor is running at 4% of slip. That means that is the full load condition. So under full load condition, the value of slip can be found out from this equation. A is equal to ns minus nr. Nr is the rotor speed. Now in the question it is asked, what is the rotor speed of this motor at full load? So ns minus nr divided by ns. We know the value of ns from here. We know the value of slip, which is 4%. Now we need to find the value of nr, that is the rotor speed at this 4% slip condition. So if we put all these values, so nr, you can write like this way, nr will be equal to ns minus s into ns, which will eventually give us ns 1 minus s. If we put all these values, n is equal to 1500, 1 minus 4% of slip means 0.04, and we'll get the value equal to 1440 RPM. You can see under full load condition, the rotor speed is lower than the synchronous speed, which was supposed to happen. Next question is, what is the rotor current frequency of this motor at full load? So at full load, we know the value of slip equal to 0.04. And we know the rotor current frequency F2 under running condition, we can say slip into F1. F1 is the supply frequency. So we can write 0.04 into 50 Hertz, which will give us the value of 2 Hertz. So the rotor current frequency under full load running condition is 2 Hertz. Next question is, what is the stator current frequency of this motor at the full load? The stator current frequency doesn't depend on the rotor speed. So the stator current frequency will be exactly equal to supply frequency. We can write stator current frequency will be equal to the supply current frequency, which is equal to 50 Hertz. Next question is, if the rotor is blocked, what will be the rotor current frequency and the stator current frequency of this motor? If the rotor is blocked, what does that mean? Rotor is not rotating. We are not allowing the rotor to rotate. Under blocked rotor condition, we know the value of slip equal to 1. How it came? Under blocked rotor condition, the value of NR equal to 0. Rotor is not moving, so NR equal to 0. So S will be NS over NS. So eventually it will give us the value of slip equal to 1. So under blocked rotor condition, the value of slip will be 1. What will be the rotor current frequency? We know the rotor current frequency F2 equal to S into F1. And under blocked rotor condition, the value of S equal to 1 into 50, that will give us 50 Hertz. Next, if the supply voltage is reduced to 100 volt, the supply voltage is reduced to 100 volt, what will be the synchronous speed of the rotating magnetic field under this condition? We know the equation of synchronous speed is Ns equal to 120 F1 over P. And this synchronous speed value doesn't depend on voltage. It only depends on the supply frequency and the number of pole per phase. So even though we are changing the voltage, the speed of the rotating magnetic field or the synchronous speed won't be changing. So under this condition, the synchronous speed will be 1500 as we got from here. So it will remain 1500 RPM like the previous one. Voltage doesn't have any effect on synchronous speed. Next question is, if the load is decreased by 10%, will the synchronous speed of this motor change? What will be the synchronous speed under this condition? First of all, if the load is decreased by 10%, that means we are changing the load. If we change the load, that doesn't mean we are changing frequency or pole, number of pole per phase. Unless or until we change these two values, the synchronous speed of this motor won't be changing. So the answer will be the synchronous speed will not change. As it is not changing, what will be the synchronous speed under this condition? The synchronous speed under this condition will remain unchanged and the value will be 1500 RPM. We can get it from here, 120 F1 over P, which is equal to 1500. I hope all of you understood how the problem is solved. Let us solve another three-phase induction motor problem. A 440 volt, three-phase 50 Hz, 4-pole Y-connected induction motor. What does Y-connected means? In the stator side, we have Y-connected configuration. Induction motor has a speed of 1490 RPM. The rotor has an impedance of 0.4 plus J4. What does it mean? R2 has a value 0.4 and X2 prime has a value 4 ohm. And rotor over stator turns ratio, that is 0.8. First of all, we need to understand what the question states. Suppose we have a three-phase induction motor This is the stator and this is the rotor. This induction motor is supplied by a three-phase source. As it is said, it is three-phase motor. 440 volt means this is the rated voltage. So from line to line, this is line 1, line 2, line 3. From line to line, we have 440 voltage. This is not phase voltage, this is line voltage, because as it is Y connected, the phase voltage and the line voltage, they won't be same. Remember, this 440 voltage is given at the primary side. So we can say E1. E1 means the voltage applied in the stator side is 440 voltage. Here the supply frequency is 50 Hz, so F1 equal to 50 Hz. Now before we proceed, we need to convert this primary voltage to the per phase voltage. So we can say E1 equal to 440 divided by root 3 volt per phase. So per phase voltage is this, which is equal to 254 voltage per phase. Here it is mentioned that rotor stator turns ratio is 0.8. So we can say E2 prime, that means induced EMF at the rotor side at standstill condition, divided by E1 equal to N2 divided by N1, that means turns in the secondary side divided by turns in the primary side, equal to 0.8. From here we can write E2 prime equal to E1 into 0.8, where E1 equal to 254 volt per phase, which can be written as 254 into 0.8 volt per phase, which is equal to 203.2 volt per phase. Now in question 1, it is asked, calculate the generated torque at 1490 rpm. That means we need to calculate the torque at the speed of 1490 rpm. So let's write the equation first. We know the torque under running condition tau r equal to 3 over twice pi ns. This ns is in rps into s into e2 prime square into r2 divided by r2 square plus sx2 prime whole square. We have figured out the value of E2 prime here, that is 203.2 volt per phase. The impedance is given as 0.4 plus J4, from where we can write, we have the value R2 equal to 0.4 ohm and X2 prime equal to 4 ohm. Ns equal to 120 F over P. If we want to get the value in RPS, we need to divide it by 60. So we'll get 120 into 50. This is F1, which means supply frequency, divided by 4, as we have 4 pole per phase, into 60, which will return us 25 RPS. Now let us put all these values, 3 over twice pi into 25 into, we need to find the value of S as well. The value of S can be written as Ns minus Nr over Ns. Here Nr is given as 1490 rpm. Either we can convert it to rps in order to equate with this 25 rps, or we can take the value of ns in rpm If we take the value of ns in rpm, we'll get 1500 rpm. Just we need to multiply it by 60. That will return us 1500 rpm. Eventually we'll get the value of s 1500 minus 1490 divided by 1500, which will give us the value s equal to 0.067. If we put all these values in this equation, 0.067 into 203.2 square into the value of R2 is 0.4 divided by 0.4 square plus 0.067 into 4 whole square. Using calculator, we can get this value. The value you will get is 13.088 Newton meter. That means at 1490 rpm, the torque that will be generated is 13.088 Newton meter. The next question is calculate starting torque. Starting torque means at a standstill condition, what is the torque? We know at starting condition the value of slip will be 1. So in order to calculate starting torque, tau of st can be written as 3 over twice pi ns. Here ns is 25 rps into s equal to 1. So we can write e2 prime square r2 divided by r2 square plus as s equal to 1. So you can write x2 prime square. Now if we put all these values and calculate, we'll get the value is equal to 19.525 Newton meter. So the running torque under 1490 rpm is 13.088 Newton meter, and the starting torque we have got 19.525 Newton meter. So till now we have got the generated torque at 1400 rpm, tau r equal to 13.088 Newton meter, and the starting torque tau st equal to 19.525 Newton meter. Now let us draw the torque speed characteristics curve, which is asked to draw in question number 5. Draw the torque speed curve. So let us draw it a bit earlier. Here ns, we have got ns equal to 1500 rpm, and initially we have got the load torque tau r, which is equal to 13.088 Newton meter, and the corresponding speed is, this is the corresponding speed nr, which is equal to 1490 rpm, and the starting torque we have got 19.525 Newton meter. This is tau or direction. Next, it is asked to calculate starting current of the rotor. From our previous lectures, we know the current, the rotor current IR, can be written as S into E2 prime divided by root over R2 square plus S x2 prime square. If we put all these values for starting current, the value of S equal to 1. So you can write E2 prime equal to 203.2 volt per phase root over R2 equal to 0.4 square plus 4 square. The value we are going to get is equal to 50.547 ampere. So the starting current is 50.547 ampere. Next question is, under running condition, if the load torque is increased to 78.87 Newton meter, will the motor run? If the motor runs, what will be the new speed of the rotor? Now here you need to understand whether the motor will run or not. It depends on the maximum torque. If this value exceeds the maximum torque, then motor will be stopped. If this value 78.87 is less than the maximum torque, then under running condition the motor will be able to run, because that falls in this stable region. So first of all, we need to calculate the maximum torque. This question will be question number 3, and next question is question number 4. We know for maximum torque under running condition, the condition for maximum torque is R2 equal to S into X2. And from here we can write S equal to R2 over X2. We have R2 is 0.4 and X2, actually X2 prime. X2 prime is 4. So the value that we are going to get is 0.1. If we put 0.1 in our torque condition, then we'll get tau max. Tau max equal to 3 over twice pi ns. We already calculated the value of ns in RPS into s, which is 0.1 for this case, E2 prime square into R2 divided by R2 square plus SX2 prime square. Now if we put all these values, we know the value of E2 prime, which was calculated in the previous page. We know the value of R2, which is 0.4. We know the value of X2 prime, which is 4, and S equal to 0.1. If we put all these values and calculate the value for tau max, we will get the tau max value is 98.5 Newton meter. So we can say this is the maximum torque. So maximum torque point is this. At this point, if we draw the line, this point is tau max, which is equal to 98.5 Newton meter. So definitely we can see 78.87 Newton meter is less than 98.5 Newton meter, but it is greater than 19.525. That means it is greater than starting torque but less than the maximum torque. So the line falls here. We are considering it here. This drawing is not accurate, but to make you understand, we have placed it here. Now under running condition, if the load is increased to 78.87 Newton meter, then the operating point will be this. In order to get this corresponding speed, we need to figure out what is the corresponding speed of the rotor, nr1. So the first question is, will the motor run? Under running condition, if we increase the load up to 78.87 Newton meter, then we can say, as it is less than the maximum torque, the motor will be able to run, motor will keep running. If the motor runs, what will be the new speed of the rotor? So in order to get the new speed, we need to employ the torque equation for this running condition. We know the torque equation. Let us name it tau r1 equal to 3 over twice pi ns into s into e2 prime square r2 divided by r2 square plus sx2 prime square. Here we know the tau r1. What is the value of tower 1? At this point, the tower 1 is given 78.87 Newton meter. Let us put this value. We can say 78.87 equal to 3 over twice pi. Ns equal to 25 rps. I'm putting all the values into s. We need to figure it out, the value of s, in order to get this speed. Into e2 square, e2 is 203.2 square, e2 prime square actually, into 0.4, which is the value of r2, 0.4 square plus s square into 4 square, as x2 prime equal to 4. Now here we can see this is the second order equation for s. That means there will be two roots for s, and we can see this line intersects in 2 points. One is here, another is here. Now once we solve it, we'll get two values of s. Which value should we take? Now we must take the value which falls at a stable region. We should not take the value which falls in the unstable region, because we are increasing the load and the point comes from here to here. So we are considering this point. This will be the operating point. So, but once we solve it, we'll get these both values. Now, as we know, the value of s decreases as we increase the value of nr, that means rotor speed. So the value of s will be lower here, the value of s will be higher here. So we need to ignore the higher value, we need to take the lower value. If we reshuffle this equation, we'll get 1261.9 s square minus 315.29 s plus 12.619 equal to 0. If we solve the equation, the roots that we are going to get, s equal to 0.1998 and s equal to 0.050. Which value of s should we take? The value that will give me this speed, where the s value is lower than this s value, because as we increase the value of rotor speed, the s value decreases. So in order to get this nr1 value, we need to take the lower one. Which one is the lower value? The value that is having 0.05. So we can say s equal to ns minus nr1 divided by ns. So nr1 can be written as ns into 1 minus s. If we put the value of ns 1500 and 1 minus 0.05, we'll get the corresponding speed of the rotor, which is equal to 1425 rpm. So here nr1 equal to 1425 rpm. I hope all of you got it. Now it may happen that this value is greater than the maximum torque. You may get this type of problem. So if this value is greater than the maximum torque that we got it here, then motor won't be able to run, motor will be stopped. In that case, you don't have to do this many calculations. Rather, you will just simply say motor won't be able to run and it will be stopped. We'll continue in the next lecture.